and terminal connected to the high output coil distributor gear. Impulse coupling. Distributor block. Magnet. Pinion gear. Capacitor. Ball bearing cam. Figure 4-17. Magneto cutaway. Mounting flange. Adjustment slot. Figure 4-19. Magneto mounting flange. Figure 4-18. A dual magneto with 2 distributors. 4-11. Low tension magneto system. High tension ignition systems have undergone many refinements and improvements in design. This includes new electronic systems that control more than just providing ignition to the cylinders. High tension voltage presents certain problems with carrying the high voltage from the magneto internally and externally to the spark plugs. In early years, it was difficult to provide insulators that could contain the high voltage, especially at high altitudes, when the air pressures were reduced. Another requirement of high-tension systems was that all weather and radio-equipped aircraft have ignition wires enclosed in shielding to prevent radio noise due to high voltages. Many aircraft were turbo-supercharged and operated at increased high altitudes. The low pressure at these altitudes would allow the high voltage to leak out even more. To meet these problems, low-tension ignition systems were developed. Electronically, the low-tension system is different from the high-tension system. In the low-tension system, low voltage is generated in the magneto and flows to the primary winding of a transformer coil located near the spark plug. There, the voltage is increased to high by transformer action and conducted to the spark plug by very short high-tension leads. Figure 4-20. The low-tension system virtually eliminates flashover in both the distributor and the harness, because the air gaps within the distributor have been eliminated by the use of a brush-type distributor. And high voltage is present only in short leads between the transformer and spark plug. Although a certain amount of electrical leakage is characteristic of all ignition systems, it is more pronounced on radio-shielded installations, because the metal conduit is at ground potential, and close to the ignition wires throughout their entire length, in low-tension systems. However, this leakage is reduced considerably because the current throughout most of the system is transmitted at a low voltage potential. Although the leads between the transformer coils and the spark plugs of a low-tension ignition system are short, they are high-tension high-voltage conductor, and are subject to the same failures that occur in high-tension systems. Low-tension ignition systems have limited use in modern aircraft because of the excellent materials and shielding available to construct high-tension ignition leads and the added cost of a coil for each spark plug with a low-tension system. FADEC system description. A FADEC is a solid-state digital electronic ignition and electronic sequential port fuel injection system with only one moving part that consists of the opening and closing of the fuel injector. FADEC continuously monitors and controls ignition, timing, and fuel mixture/delivery/injection, and spark ignition as an integrated control system. FADEC monitors engine operating conditions, crankshaft speed, top, starting vibrator magneto switch left magneto, L2, R3, R2, R1, off, LR both, C2, T1, V1, L4, L1, main breaker, retard breaker, spark plug, C1, off S3, on, L3, right magneto, C3, main breaker, L5, starter solenoid, T2, spark plug, R4, S, figure 4-20. Simplified low-tension ignition system schematic, 4-12. Dead center position, the induction manifold pressure, and the induction air temperature, and then automatically adjusts the fuel-to-air ratio mixture and ignition timing accordingly for any given power setting to attain optimum engine performance. As a result, engines equipped with FADEC require neither magnetos nor manual mixture control. This microprocessor-based system controls ignition timing for engine starting, and varies timing with respect to engine speed and manifold pressure. Figure 4-21. PowerLink provides control in both specified operating conditions and fault conditions. The system is designed to prevent adverse changes in power or thrust. In the event of loss of primary aircraft supplied power, the engine controls continue to operate using a secondary power source, SPS. As a control device, the system performs self-diagnostics to determine overall system status and conveys this information to the pilot by various indicators on the Health Status Annunciator, HSA, panel. PowerLink is able to withstand storage temperature extremes, and operate at the same capacity as a non-FADEC equipped engine in extreme heat, cold, and high humidity environments. Low voltage harness. The low voltage harness connects all essential components of the FADEC system. Figure 4-22. This harness acts as a signal transfer bus interconnecting the electronic control units, UCUS, with aircraft power sources, the ignition switch, speed sensor assembly, SSA, temperature and pressure sensors, the fuel injector coils and all sensors, except the SSA and fuel pressure and manifold pressure sensors, are hardwired to the low voltage harness. This harness transmits sensor inputs to the UCUS through a 50-pin connector. The harness connects to the engine-mounted pressure sensors via CAN and plug connectors. The 25-pin connectors connect. Figure 4-22. Typical 6-cylinder engine electronic control and low-voltage harness. Figure 4-21. PowerLink system components. 4-13. The harness to the speed sensor signal conditioning unit. The low-voltage harness attaches to the cabin harness by a firewall-mounted data port through the same cabin harness/bulkhead connector assembly. The bulkhead connectors also supply the aircraft electrical power required to run the system. The ECU is at the heart of the system, providing both ignition and fuel injection control to operate the engine with the maximum efficiency realizable. Each ECU contains 2 microprocessors, referred to as a computer, that control 2 cylinders. Each computer controls its own assigned cylinder, and is capable of providing redundant control for the other computer's cylinder. The computer constantly monitors the engine speed and timing pulses developed from the camshaft gear as they are detected by the SSA. Knowing the exact engine speed and the timing sequence of the engine, the computers monitor the manifold air pressure and manifold air temperature to calculate air density and determine the mass airflow into the cylinder during the intake stroke. The computers calculate the percentage of engine power based on engine revolutions per minute, RPM, and manifold air pressure. From this information, the computer can then determine the fuel required for the combustion cycle for either best power or best economy mode of operation. The computer precisely times the injection event, and the duration of the injector should be on time for the correct fuel-to-air ratio. Then, the computer sets the spark ignition event and ignition timing, again based on percentage of power calculation. Exhaust gas temperature is measured after the burn to verify that the fuel-to-air ratio calculations were correct for that combustion event. This process is repeated by each computer for its own assigned cylinder on every combustion/power cycle. The computers can also vary the amount of fuel to control the fuel-to-air ratio for each individual cylinder to control both cylinder head temperature, CHT, and exhaust gas temperature, ECT. Electronic Control Unit, ECU. An ECU is assigned to a pair of engine cylinders. Figure 4-23, DIPs control the fuel mixture and spark timing for their respective engine cylinders. ECU1 controls opposing cylinders 1 and 2. ECU2 controls cylinders 3 and 4. And ECU3 controls cylinders 5 and 6. Each ECU is divided into upper and lower portions. The lower portion contains an electronic circuit board, while the upper portion houses the ignition coils. Each electronic control board contains 2 independent microprocessor controllers that serve as control channels. During engine operation, one control channel is assigned to operate a single engine cylinder. Therefore, one ECU can. Figure 4-23. Electronic Control Unit. Control 2 engine cylinders. One control channel per cylinder. The control channels are independent, and there are no shared electronic components within one ECU. They also operate on independent and separate power supplies. However, if one control channel fails, the other control channel in the pair within the same ECU is capable of operating both its assigned cylinder and the other opposing engine cylinder as backup control for fuel injection and ignition timing. Each control channel on the ECU monitors the current operating conditions and operates its cylinder to attain engine operation within specified parameters. The following transmit inputs to the control channels across the low-voltage harness. 1. Speed sensor that monitors engine speed and crank position. 2. Fuel pressure sensors. 3. Manifold pressure sensors. 4. Manifold air temperature, MAT, sensors. 5. CHT sensors. 6. ECT sensors. All critical sensors are dually redundant with one sensor from each type of pair connected to control channels in different ECUs. Synthetic software default values are also used in the unlikely event that both sensors of the redundant pair fail. The control channel continuously monitors changes in engine speed, manifold pressure, manifold temperature, and fuel pressure based on sensor input relative to operating conditions to determine how much fuel to inject into the intake port of the cylinder. Power length ignition system. The ignition system consists of the high-voltage coils atop the ECU, the high-voltage harness, and spark plugs. Since there are 2 spark plugs per cylinder on all engines, a 6-cylinder engine has 12 leads and 12 spark plugs. One end of each lead on the high-voltage harness attaches to a spark plug, and the other end of the lead wire attaches to the spark plug towers on. 4-14. Each ECU. The spark tower pair is connected to opposite ends of one of the ECU's coil packs. 2 coil packs are located in the upper portion of the ECU. Each coil pack generates a high-voltage pulse for 2 spark plug towers. One tower fires a positive polarity pulse, and the other of the same coil fires a negative polarity pulse. Each ECU controls the ignition spark for 2 engine cylinders. The control channel within each ECU commands one of the 2 coil packs to control the ignition spark for the engine cylinders. Figure 4-24. The high-voltage harness carries energy from the ECU spark towers to the spark plugs on the engine. For both spark plugs in a given cylinder to fire on the compression stroke, both control channels must fire their coil packs. Each coil pack has a spark plug from each of the 2 cylinders controlled by that ECU unit. The ignition spark is timed to the engine's crankshaft position. The timing is variable throughout the engine's operating range and is dependent upon the engine load conditions. The spark energy is also varied with respect to the engine load. Note: engine ignition timing is established by the ECUs and cannot be manually adjusted. During engine starting, the output of a magneto is low because the cranking speed of the engine is low. This is understandable when the factors that determine the amount of voltage induced in a circuit are considered. To increase the value of an induced voltage, the strength of the magnetic field must be increased by using a stronger magnet, by increasing the number of turns in the coil, or by increasing the rate of relative motion between the magnet and the conductor. Since the strength of the rotating magnet and the number of turns in the coil are constant factors in magneto-ignition systems, the voltage produced depends upon the speed at which the rotating magnet is turned. When the engine is being cranked for starting, the magnet is rotated at about 80 rpm. Since the value of the induced voltage is so low, a spark may not jump the spark plug gap. To facilitate engine starting, an auxiliary device is connected to the magneto to provide a high ignition voltage. Ordinarily, such auxiliary ignition units are energized by the battery and connected to the left magneto. Reciprocating engine starting systems normally include one of the following types of auxiliary starting systems. Booster coil, older style, electronic control unit 1. Top spark plug. Channel 1. Coil pack 1. Cylinder no. 1. Bottom spark plug. Channel 2. Top spark plug. Coil pack 2. Cylinder no. 2. Bottom spark plug. Figure 4-24. Ignition control. 4-15. Starting vibrator, sometimes called shower of sparks, impulse coupling, or electronic ignition systems. During the starting cycle, the engine is turning very slowly compared to normal speed. The ignition must be retarded or moved back to prevent kickback of the piston trying to rotate opposite normal rotation. Each starting system has a method of retarding the spark during starting of the engine. Booster coil. The booster coil assembly, used mainly with older radial engine ignition systems, consists of 2 coils wound on a soft iron core, a set of contact points, and a condenser. Figure 4-25, the booster coil is separate from the magneto and can generate a series of sparks on its own. During the start cycle, these sparks are routed to the trailing finger on the distributor rotor, and then to the appropriate cylinder ignition lead. The primary winding has one end grounded at the internal grounding strip, and its other end connected to the moving contact point. The stationary contact is fitted with a terminal to which battery voltage is applied when the magneto switch is placed in the start position, or automatically applied when the starter is engaged. The secondary winding, which contains several times as many turns as the primary coil, has one end grounded at the internal grounding strip, and the other terminated at a high-tension terminal. The high-tension terminal is connected to an electrode in the distributor by an ignition cable. Since the regular distributor terminal is grounded through the primary or secondary coil of a high-tension magneto, the high voltage furnished by the booster coil must be distributed by a separate circuit in the distributor rotor. This is accomplished by using 2 electrodes in one distributor rotor. The main electrode, or finger, carries the magneto output voltage. The auxiliary electrode or trailing finger distributes only the output of the booster coil. The auxiliary electrode is always located so that it trails the main electrode, thus retarding the spark during the starting period. Figure 4-26 illustrates. In schematic form, the booster coil components shown in figure 4-25. In operation, battery voltage is applied to the positive plus terminal of the booster coil through the start switch. This causes current to flow through the closed contact points to the primary coil and ground. Figure 4-26. Current flow through the primary coil sets up a magnetic field about the coil that magnetizes the coil core. As the core is magnetized, it attracts the movable contact point, which is normally held against the stationary contact point by a spring. As the movable contact point is pulled toward the iron core, the primary circuit is broken, collapsing the magnetic field that extended about the coil core. Since the coil core acts as an electromagnet only when current flows in the primary coil, it loses its magnetism as soon as the primary coil circuit is broken. This permits the action of the spring to close the contact points, and again complete the primary contact spring. External ground through mounting bolt. To starter side of start switch. To battery negative to booster terminal of magneto. Vibrator stationary contact. Vibrator moving contact. Access screw. Primary winding condenser. Cover. Wire core. Internal grounding strip. Figure 4-25. Booster coil. 4-16. Plus. Condenser. Movable contact spring. Stationary contact point. Moving contact point. Primary winding. Coil core. Secondary winding. Internal grounding strip. Body flyweights. Figure 4-26. Booster coil schematic. Coil circuit. This remagnetizes the coil core, and again attracts the movable contact point, which again opens the primary coil circuit. This action causes the movable contact point to vibrate rapidly, as long as the start switch is held in the closed, or on, position. The result of this action is a continuously expanding and collapsing magnetic field that links the secondary coil of the booster coil, with several times as many turns in the secondary as in the primary. The induced voltage that results from lines of force linking the secondary is high enough to furnish ignition for the engine. The condenser, which is connected across the contact points, has an important function in this circuit. Figure 4-26. As current flow in the primary coil is interrupted by the opening of the contact points, the high self-induced voltage that accompanies each collapse of the primary magnetic field surges into the condenser. Without a condenser, an arc would jump across the points with each collapse of the magnetic field. This would burn and pit the contact points, and greatly reduce the voltage output of the booster coil. The booster coil generates a pulsating DC in the primary winding that induces a high voltage spark in the secondary windings of the booster coil. Impulse coupling. Many opposed reciprocating engines are equipped with an impulse coupling as the auxiliary starting system. An impulse coupling gives one of the magnetos attached to the engine, generally the left, a brief acceleration that produces an intense spark for starting. This device consists of a cam and flyweight assembly, spring, and a body assembly. Figure 4-27. The assembled impulse coupling is shown installed on a typical magneto in Figure 4-28. The magneto is flexibly connected through the impulse coupling by means of the spring so that at low speed the cam, spring, Figure 4-27. Parts of an impulse coupling. Magneto is temporarily held. Figure 4-29. The flyweight, because of slow rotation, catches on a stud or stop pins, and the magneto spring is wound as the engine continues to turn. The engine continues to rotate until the piston of the cylinder to be fired reaches approximately a top dead center position. At this point, the magneto flyweight contacts the body of the impulse coupling and is released. The spring kicks back to its original position, resulting in a quick twist of the rotating magnet of the magneto. Figure 4-30. This, being equivalent to high-speed magneto rotation, produces a spark that jumps. 4-17. Body hits flyweight. Stop pin. Impulse coupling. Figure 4-30. Flyweight contacts body, releasing impulse coupling to spin. Figure 4-28. Impulse coupling on a magneto engages stop pin. Figure 4-29. Flyweights engage stop pins. The gap at the spark plug electrodes. The impulse coupling has performed two functions, rotating the magneto fast enough to produce a good spark, and retarding the timing of the spark during the start cycle. After the engine is started and the magneto reaches a speed at which it furnishes sufficient current, the flyweights in the impulse coupling fly outward due to centrifugal force or rapid rotation. This action prevents the two flyweight coupling members from contact with the stop pin. That makes it a solid unit, returning the magneto to a normal timing position relative to the engine. The presence of an impulse coupling is identified by a sharp clicking noise as the crankshaft is turned at starter cranking speed past top center on each cylinder. A problem that can arise from impulse couplings is that the flyweights can become magnetized and not engage the stop pins. Congealed oil or sludge on the flyweights during cold weather may produce the same results. This prevents the flyweight weights from engaging the stop pins, which results in no starting spark being produced, where can cause problems with impulse couplings. They should be inspected and any maintenance should be performed as set forth by the manufacturer. Another disadvantage of the impulse coupling is that it can produce only one spark for each firing cycle of the cylinder. This is a disadvantage, especially during adverse starting conditions. Even with these disadvantages, the impulse coupling is still in wide use. High-tension retard breaker vibrator. To provide for more spark power during the starting cycle, the shower of sparks system was developed, which provides several sparks at the spark plug electrodes during starting. The starting vibrator, or shower of sparks, consists essentially of an electrically operated vibrator, a condenser, and a relay. Figure 4-31. These units are mounted on a base plate and enclosed in a metal case. The starting vibrator, unlike the booster coil, does not produce the high ignition voltage within itself. The function of this starting vibrator is to change the DC of the battery into a pulsating DC and deliver it to the primary coil of the magneto. Closing the ignition switch energizes the starter solenoid and causes the engine to rotate. At the same time, current also flows through the vibrator coil and its contact points. Current flow in the vibrator coil sets up a magnetic field that attracts and opens the vibrator points. When the vibrator points open, current flow in the coil stops, and the magnetic field that attracted the movable vibrator contact point disappears. This allows the vibrator points to close and 4-18. L. Starting vibrator. Magneto switch left magneto. R. R3. R2. LR both. Off L. Switch. C2. L2. V1. R1. L in. GRD. Main breaker. T1. L1. Retard. R. Retard breaker. C1. Right magneto. Off S1. On. Switch. L3. C3. Main breaker. T2. R4. S. Figure 4-31. High-tension retard breaker magneto and starting vibrator circuit. Again permits battery current to flow in the vibrator coil. This completes a cycle of operation. The cycle, however, occurs many times per second, so rapidly that the vibrator points produce an audible buzz. Each time the vibrator points close, current flows to the magneto as a pulsating DC. Since this current is being interrupted many times per second, the resulting magnetic field is building and collapsing across the primary and secondary coils of the magneto many times per second. The rapid successions of separate voltages induced in the secondary coil produces a shower of sparks across the selected spark plug or gap. The retard breaker magneto and starting vibrator system is used as part of the high-tension starting system on many types of aircraft. Designed for 4- and 6-cylinder ignition systems, the retard breaker magneto eliminates the need for the impulse coupling in light aircraft. This system uses an additional breaker to obtain retarded sparks for starting. The starting vibrator is also adaptable to many helicopter ignition systems. A schematic diagram of an ignition system using the retard breaker magneto and starting vibrator concept is shown in figure 4-31. With the magneto switch in the both position and the starter switch S1 in the on position, starter solenoid L3 and coil L1 are energized. Closing relay contacts R4, R1, R2, and R3. R3 connects the right magneto to ground, keeping it inoperative during starting operation. Electrical current flows from the battery through R1, vibrator points V1, coil L2, through both the retard breaker points, through R2, and the main breaker points of the left magneto to ground. The energized coil L2 opens vibrator points V1, interrupting the current flow through L2. The magnetic field about L2 collapses, and vibrator points V1 close again. Once more, current flows through L2, and again V1 vibrator points open. This process is repeated continuously, and the interrupted battery current flows to ground through the main and retard breaker points of the left magneto. Since relay R4 is closed, the starter is energized and the engine crankshaft is rotated. When the engine reaches its normal advance firing position, the main breaker points of the left magneto begin to open. The interrupted surges of current from the vibrator can still find a path to ground through the retard breaker points, which do not open until the retarded firing position of the engine is reached. At this point in crankshaft travel, the retard points open. Since the main breaker points are still open, the magneto primary coil is no longer shorted, and current produces a magnetic field around T1. 4-19. Each time the vibrator points V1 open, current flow through V1 is interrupted. The collapsing field about T1 cuts through the magneto coil secondary, and induces a high voltage surge of energy used to fire the spark plug. Since the V1 points are opening and closing rapidly and continuously, a shower of sparks is furnished to the cylinders when both the main and retard breaker points are open. After the engine begins to accelerate, the manual starter switch is released, causing L1 and L3 to become de-energized. This action causes both the vibrator and retard breaker circuits to become inoperative. It also opens relay contact R3, which removes the ground from the right magneto. Both magnetos now fire at the normal advanced running degrees of crankshaft rotation before top dead center piston position. Low tension retard breaker vibrator. This system, which is in limited use, is designed for light aircraft reciprocating engines. A typical system consists of a retard breaker magneto, a single breaker magneto, a starting vibrator, transformer coils, and a starter and ignition switch. Figure 4-32. To operate the system, place the starter switch S3 in the on position. This energizes starter solenoid L3 and coil L1. Closing relay contacts R1, R2, R3, and R4. With the magneto switch in the L position, current flows through R1, the vibrator points, L2, R2, and through the main breaker points to ground. Current also flows through R3 and the retard breaker points to ground. Current through L2 builds up a magnetic field that opens the vibrator points. Then, the current stops flowing through L2, or closing the points. These surges of current flow through both the retard and main breaker points to ground. Since the starter switch is closed, the engine crankshaft is turning. When it has turned to the normal advance or running ignition position, the main breaker points of the magneto open. However, current still flows to ground through the closed retard breaker points. As the engine continues to turn, the retard ignition position is reached, and the retard breaker points open. Since the main breaker points are still open, current must flow to ground through coil L4, producing a magnetic field around the coil L4. As the engine continues to turn, the vibrator breaker points open, collapsing the L4 magnetic field through T1 primary, inducing a high voltage in the secondary of T1 to fire the spark plug. When the engine fires, the starter switch is released, de-energizing L1 and L3. This opens the vibrator circuit and retard breaker point circuit. The ignition switch is then turned to the both position, permitting the right magneto to operate in time with the left magneto. Starting vibrator magneto switch left magneto. L2, R3, R2, R1, off. LR both. C2, T1, V1, L4, L1, main breaker, retard breaker, spark plug, C1, off S3, on, L3, right magneto, C3, main breaker, L5, starter solenoid, T2, spark plug, R4, S, figure 4-32, low tension retard breaker magneto and starting vibrator circuit, 4-20.